This is a spirogram taken from a 13.5 liter column spirometer. They also make the 7 liter spirometer. So for the 13, we'll need to double the figures on the paper. So just keep that in mind. This is a typical spirogram with tidal volumes, the inspiratory, and then the hold, and then the fast exhalation with a forced exhalation for at least 6 seconds. Now, the criteria for a test to be valid, we need a maximum effort with no cough or glottic closure. These are often seen by little ripples on the tracings. Less than 100 milliliter difference in the tidal volumes. A plateau is observed on inspiration, hold, and on the exhalation, which on this tracing was very apparent. A back extrapolation of less than 150 milliliters or 5%. And this is the takeoff point, needs to be very crisp and sharp, so there isn't a lag there of 150 milliliters or more. We need to attain at least 6 seconds. So the exhalation needs to exceed 6 seconds, and this one approximately 7.5 seconds. And 3 acceptable spirograms are within 200 milliliters of each other. I have only shown one here just for simplicity's sake. Now, some of the measurements we might take, we might look at the inspiratory capacity, which would be measured from the bottom of a normal exhalation to the top of the inspired part. Now, typically, as I look at this chart, we would take about 3.9 liters is about where the top is, 3.978 liters, which was calculated. Here's 4 liters, a little less. And we started at the bottom of an exhalation of around 1,850 milliliters. Then that would give us about 2.178 liters. We would need to double for the paper, giving us about 4.2 liters, and then we have to make the correction for the temperature, which was at 19 degrees Celsius, and this is the correction factor to convert that volume to BTPS, or body temperature, this giving us a value of about 4.7 liters from here to there. Now, from the same point going down, we would do the same thing, the 1850 that we used as the bottom of the normal exhalation, from the very last second we did in our impulse. Again, we double for the paper, giving us about 1.2 liters, doing our temperature correction, and giving us approximately 1.35 liters for the expiratory reserve volume. When we look at the percents, when we add these together of the vital capacity, we could see the inspiratory was about 77% and the expiratory was about 22% in this example. Typically, there will be about 25-75. Now, once we've gotten our tracing, one of the first things we want to do is look at all 3 tracings that we would typically do and determine which one has the highest combination of forced vital capacity and forced expiratory volume in 1 second. And we will note which one of the 3 tracings had the highest of each value. But we'll then take the sum of the 2, and we'll use that one for all further evaluations. Forced vital capacity, we're going to start at the very beginning of the exhalation, and we're going to measure it to the very end. And when we did that, we started at 3.78 liters. The very finish was 1.242. We double for the paper, and again, we got about 5.4 liters. Then we have to correct for the temperature. That gave us a forced vital capacity on this subject of about 6.06 liters. The forced expiratory volume in 1 second. Well, as the drum is spinning, each of these lines are 1 second apart. And to get in 1 second from the initial exhalation, we would measure the distance from this line and add it over here to the other side and measure from that point. And when we did that, 3.978 liters was the start of the exhalation, and in 1 second, they were at 1.905. Again, we double for the paper, and we multiply by the temperature conversion, and we ended up with 4.59 liters. Now, once we've gotten those 2 and we've determined which one of our 3 tracing has the highest combination, we'll go through and do the rest of the computations, the forced expiratory volume in 2 seconds. We measured 1 second. Now we would measure 2 seconds and 3 seconds and go through very similar computations to find out how much air was exhaled in 2 and 3 seconds. Typically, in the FEV1, a person would roughly 80% of their vital capacity. In our tracing, we did about 75.7. Typically, at about the FEV2, they'd be around 92, 93%, and typically about 95, 97% in the FEV3. Other readings we might look at. forced expiratory flow from the 25 to 75% range. So on this one, we're going to actually figure out what our total vital capacity was from the top to the bottom, which was 2.736 liters. We don't have to do all of the doubling for the paper or the temperature conversion yet, but we're going to take 25% of that value from here to here, and we're going to put a point there. And that point will tell us at the 25% level from the top, that is the 25% of the vital capacity, and then we're going to go 25% up from the bottom. That will leave us the middle 50%. And when we take 25% from the top, we'll put the liters at about 3.29 liters, and we'll find our spot, and we'll put it there at 3.29 liters. And then we'll find where it is 75%, where we're going to go up from the bottom to about 1.93 liters, and we put a point there at 1.93 liters, and we'll take a line and connect the two until it overlaps one of the second lines. And when we do that, we ended up with it intersecting at about 4.02 on one side and about 2.27 on the other side of the line, giving us about 3.5 liters when we double for the paper and the temperature correction, and we have our 3.87 liters. This gives us an idea of the airflow and the patency of the middle airways. Another one we might do, and we used to do this for peak flow measurements, since a computer can get that one instant. Here we had to go where the slope of the line was the fastest and the exhaling is the quickest. And we put a little line at 200 milliliters down, and we put another line at 1,200 milliliters down. Now, because we have to double for the paper, that 200, 1,200 is actually 100, 600. And I took 100 milliliters off of the top and 600 milliliters off the top, and this gave us our 2 points, which we actually have put in here very faintly. We connected the two lines again using a straight edge, and when we connected the two lines, we see where they intersected the lines, and at about 4.59 on one side and about 1,400 on the other. We double for the paper, the temperature correction. We ended up with a peak flow of around 7.06 liters. Our last measurement we looked at was the maximum voluntary ventilation. Here we used another set of needles on the spirometer, and we're using the pen that measured the peak expiratory or maximum voluntary ventilation. And as the drum spun one full rotation, this was measuring our breaths, and you could see it started here, and each breath it went a little higher until it came out right here. And we measured the difference between here and here, and that would be in 15 seconds. Once we get that amount of air, we double for the paper, and then we have to multiply that 15 seconds, which is 1/4 of a minute, times the 1/25 of a breath this measures. Well, 4 times 25 will give us 100. And we'll just basically move the decimal points over a couple points, and then we'll correct for the temperature, and we have our liters on maximum voluntary ventilation. So this would be a complete pulmonary evaluation, and using equipment that I think we can say is very accurate, and probably use this to even calibrate a lot of the materials we use today. One thing that we do have an improvement is often today we can use a peak flow meter to measure the peak flows, because the FEF 200, 1200 test that we used to use back then, the numbers are significantly lower, and with advances in technology, we're able to use, let's say, a Wright's peak flow meter and get that number also. So I hope you enjoyed this presentation. It's kind of rare to see this kind of equipment and actually see a spirogram being done. Thank you.